I'm Dietrich, and I'm the Group 1 lead on the Rankine cycle, Experiment 5. A little bit of background: was proposed by William Rankine, who was a Scottish civil engineer. He lived around the 1800s, and the premise that he proposed was this heat engine that would operate with water, and that consisted of a pump, a boiler, a turbine, and a condenser. The premise of a heat engine is that there's heat going in and heat coming out, and if you take the difference between those two, you can get some work, some network of a system. The cycle, if you were to look right here, if the picture was still here, you can see the cycle itself. Essentially, it's the pump that operates with the working fluid is water, so it's going to act like the heart of the system, and it's going to pump the water up towards the boiler. The boiler is going to heat up the water and turn it into steam, and then the steam is then shot out of a nozzle towards the turbine, and the turbine will have these sort of paddle wheels that will be pushed and turned, that the flow of steam into rotational kinetic energy. You can think of it kind of like how a windmill operates. Then the water needs to be condensed back down into water before it gets back to the pump, or else the pump will cavitate and damage the pump itself. The experiment apparatus, so just imagine the experiment apparatus is here, and I guess I could skip this part, but essentially you would see that there's three main components. There's the condenser, there would be the turbine, and also the boiler. They listed everything, including the wheels of the tray that has the entire system, but there isn't the pump itself, which I thought was a bit strange. Real versus ideal. The ideal, obviously, it's going to not account for any losses. These losses mainly occur as heat losses within the pump and the turbine itself, and of course, because of fluid friction within the pipes. This would actually lower the pressure, and so the pump then has to work a little bit more and push it up to a higher pressure. Here's the formulas. You can see that it really operates under the first law for each device. It's going to kind of simplify down into the heat in minus the work out is equal to the difference in enthalpy. Because it's steady flow, you can actually just cancel out mass on both sides and turn it to the mass-specific terms. The pump itself, because it is water and because it can be a compressible fluid by the time it goes to the pump, you can just do PdV. You'll also notice that for the condenser and for the turbine, it uses the initial minus the previous enthalpies. This is because the condenser and the pump will actually and the turbine will have energy out, so it's going to be work for the turbine and heat for the condenser. And then of course you have your thermal efficiency, which is going to be the net work over the heat in. For any kind of efficiency, you can just use what you're going to look for over what you're going to use. And of course you can use the enthalpy terms, and that should give you what the efficiency will be in terms of. I was asked to do an example calculation. So this was from the thermal book. If you were given the pressure before and after the pump, and then you were I decided to cut you guys some slack and just give you the heat that's going into the system. You're given S3, H3, but you aren't given any information about S4. Again, the diagram is gone, but you would see that it would end up inside of the vapor dome, which means that it's going to be some kind of saturated vapor for S4. So for calculating the efficiency, all you need is just the difference between the pump work and the turbine work, and then that over Q in, which you're already given. For the pump work, you can just do PdV. You can assume that there's specific water at room temperature, and you can say that's about 0.00101, and then minus the two pressures, and that will give you about 2 kilojoules per kilogram. And of course, you have the work of the turbine. The work of the turbine is a bit more tricky, but you can assume that it's isentropic because this is an ideal system. So you can just equate S3 and S4 and find equality. And then to find the H4, and then use the differences in H3 and H4 to give you the work that you get out of the turbine. Once you have the two works, you can just subtract the work of the pump minus the work of the turbine, and that will give you what you need to divide by the Hn, and that will give you about 30.3 for a Rankine cycle. For the conclusion, try to notice in the report the losses and how they're accounted for. Try to notice the energy that the pump would use, although the pump isn't listed up there, and then the efficiency of maybe ideal versus the actual system.